So the topic is the stability of the nuclei. Now look, a stable nucleus is one which has very low probability of decay. I mean, the chance of decay of the stable nucleus is rare. And the less stable or the least stable nuclei are more likely to decay or disintegrate. Now, there is a important thing to check the stability of the nucleus, and that is the binding energy per nucleon. So binding energy per nucleon is important to check the stability of any nucleus. Higher the binding energy per nucleon, less the chance to decay. So stability of the any nucleus does not depend on the total binding energy. It depends on only the binding energy per nucleon. For example, hydrogen and uranium, both are unstable. The binding energy of the hydrogen is very small, and the binding energy of the uranium is large. And similarly, the iron, the binding energy is small as compared to the uranium, but the binding energy per nucleon of the iron is larger than the binding energy per nucleon the uranium. That's why the iron is more stable as compared to the uranium. In this graph, this is the mass number, this is the binding energy per nucleon, and the graph is like this. The most stable element is the iron, and its mass number is 56. This is hydrogen, and here is uranium. Look, uranium and hydrogen both are unstable. Its binding energy is too large, but binding energy per nucleon is small. That's why the uranium is unstable. And uranium gets the stability after fission process, and the hydrogen will get stability after fusion process. So there will be the mass deficit due to decrease in the mass, and here is a mass deficit due to increase in the mass. So both are gaining stability. Their binding energy per nucleon increasing, less increase in the binding energy nucleon per nucleon for the uranium, and the more increase in the binding energy per nucleon of the hydrogen for the same delta M. So the hydrogen is more stable as compared to uranium after same mass deficit. So delta M and the delta M for the uranium same, but this process fission is powerful approximately 10 times, 6 times than the fission. So fission is less power reaction and the fusion is more powerful reaction. Now the question is, what is fission and what is fusion? Look, fusion first. When two or more light nuclei are combined together to form a heavy nucleus along with the release of the energy, then process is called nuclear fusion along with the release of energy. Suppose the equation is H12 plus H12 because the lightermost nuclei is hydrogen. When both hydrogen nuclei are combined, another hydrogen is formed along with the release of the neutron and some energy. And sometimes H11, they form the helium along with the energy. So when two or more light nuclei are combined together to form a heavy nucleus along the release of the energy, then the process is called nuclear fusion. Look, this hydrogen, both nuclei are positive. So initially, we have to supply some energy to conduct this nuclear fission to overcome the repulsion. So this nuclear fission is not the simple process. First of all, we have to provide some energy to overcome the repulsion between the two hydrogen nuclei. Then they will collide with each other and they will form a heavy nucleus along with the release of energy. So this energy is too large as compared to the supplied energy. And similarly here, we have to supply first energy and this energy is released. So this energy is greater than the supplied energy. To overcome the repulsion, first we have to supply some energy. So naturally, it's not possible. So this process is only occurring when there is a high temperature. High temperature increases the kinetic energy, and this energy overcomes the repulsion. And after this, there is a fusion. So naturally, this process is occurring at the surface of the sun. So the very high temperature, approximately 10 power 5 Kelvin. So minimum temperature which is required is 10 power 5 Kelvin. So when we will add 273, no difference, approximately 10 power 5 degrees Celsius. So this huge temperature is required, right, to overcome the repulsion force, to provide the kinetic energy to these two hydrogen nuclei to fuse together. Okay, so they are traveling towards each other with huge amount of the kinetic energy. So the whole of the kinetic energy is converted into the nuclear energy according to formula E is equal to mc square, and this release energy is too large as compared to the supplied energy. So naturally, this is occurring at the surface of the sun because to conduct this reaction, huge energy is required, large amount of the kinetic energy is required with the help of large, huge temperature, approximately temperature close to the sun. So naturally, it is only happening at the surface of the sun. Now come to the fission. Fission process is simple. When a heavy nucleus is broken into two or more light nuclei along with the release of the energy, then the process is called fission. So nuclear fission is actually the splitting of the heavy nucleus into two lighter nuclei of approximately the same mass. For example, when uranium 92 235 interacts with a neutron, uranium 92 236 is formed, and then this uranium splits into barium and krypton, the barium 56, I think 141, and the krypton 3692 plus 3 neutrons along with the energy in the form of heat and radiation. So look, this uranium 236 is splitting into two light nuclei, barium and krypton, along with the release of energy. So the process occurs due to the collision of the neutron and this. Neutron is neutral. And the uranium is already unstable. So no energy is supplied for this reaction to happen. So no kinetic energy, no temperature, right? No energy is required. So this is the natural process. So energy, zero energy is supplied here, and a huge amount of the energy is released, but this energy is smaller than the output energy of the fusion. So here the nucleus is unstable, already unstable. This neutron is attracted by the nucleus. So due to the collision, it splits into two light nuclei, krypton and barium, along with the release of energy. So the binding energy per nucleon of the barium and krypton is greater than the binding energy of uranium 235 and 236. So both are unstable, but these two are stable. Now, these three neutrons are emitted. For example, this is the uranium. One neutron hits this. Three neutrons are emitted, neutron, 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 and they will collide with three further uranium. Three neutrons are emitted. So this is a chain reaction. An uncontrolled chain reaction is used in, yes, weapons. But when out of three, when two neutrons are captured by the cadmium or the boron, one neutron is allowed to conduct the reaction and two are stopped, one allowed to capture or conduct the reaction, three are emitted, two stopped, one continues the process, then this is called the controlled fission reaction, which is used in nuclear power stations to generate electricity. So fission, uncontrolled and controlled. So this is chain reaction. So controlled reaction is used in nuclear power reaction, nuclear power stations for the generation of the electricity. Now, do remember the mass of the alpha particle is always less than the total mass of the two individual protons and two individual neutrons. For example, we have protons and we have neutrons, and their masses are taken, so they are 4m naught, because the mass of proton, mass of the neutron is called rest mass, m naught. But when they are the part of the nucleus, mean alpha particle or the helium nucleus, their mass is represented by 4u, and the 4u is always smaller than the 4m naught. Reason, the difference of the mass, which is called the delta M, it is converted into energy, and the energy formula is mc square, and this becomes the binding energy among the nucleon, which keeps the proton neutron together inside the nucleus. So here, when they are outside the nucleus, no need for the binding energy, so their mass is large. Now, for example, there is a reaction, helium, which is alpha particle, 2, 4, and nitrogen, 7, 14, and oxygen, 8, 17 is formed along with the release of the proton. So with the combination of alpha and this nitrogen, another nucleus is formed along with the release of the proton. Now suppose data says the mass of the proton is 1.00728 U, and the mass of the helium, He24, is 4.00260 U, and the mass of the nitrogen, N714, is 14.00307 U, and the oxygen, O817, not 16 isotope, and 16.99913 U. What is isotope? Isotope is actually the nuclei of the same element having same number of protons but different number of neutrons. Now, if the question is calculate the mass change in U associated with this reaction, so we have to find delta M in terms of the U. So look, mass deficit, the mass of this and the mass of this, yes, both are added. Then mass of this, both are added. So the sum of this and the sum of this, we will get the difference here. So the sum of the reactants and the sum of the product, the difference will be the M. You have to solve this. Calculate the energy associated with this mass. For the second, we will write the delta mc square. Before calculating this, you have to convert U into kg, which is 1.66 into 10 power minus 27 kg. And suppose the question is, suggest and explain why for this reaction to occur, the helium-4 nucleus must have a minimum speed. Helium-4 nucleus. Look, this is nucleus positively charged. This is nucleus positively charged. Positive will repel. To overcome this repulsion, the alpha particle must have some kinetic energy, right, to approach the neutron nucleus and to react it, right? So both are positively charged. They are repelling each. So one of them must have some kinetic energy to overcome that repulsion. Now, during the decay, parent nucleus disintegrates. Parent element decay. For example, the parent element is decaying exponentially. At the same time, the daughter nucleus is forming, is increasing in number exponentially. So this is the parent nucleus. Suppose initially is unknot and the daughter nucleus is 0, right? When this is decreasing, so it is converting into the daughter nucleus. So daughter nucleus mass is increasing, number is increasing. So this is the graph between the parent nucleus and the daughter nucleus. And do remember the next part. In this equation, the proton has mass, yes, in this reaction, but it has no binding energy because this is not the part of the nucleus. Neutron, proton, if not the part of the nucleus, yes, it has mass, but it has no share in the binding energy because the binding energy is only required for the nucleus. When proton and neutron are not the part of the nuclei, they have no binding energy, they have just the mass.